So again, welcome everyone to the second tutorial of the day. In the morning, or was it in the afternoon? Yeah, it was in the afternoon from Rwanda here. Sebastian shed a little bit of light on decision trees. So, but now I will be giving a bit of presentation about XGBoost. So all these decision tree, XGBoost, these are a kind of meta algorithm that is under the general context of assembles. So that is why you see assembles on my slides now. So I'm going to take it from here before actually going into XGBoost itself. So whenever you can, if you can hear me at some point in time, or you can see my slide, please, you can unmute and tell me, or just type in the message. But it's better to unmute and tell me so that I can realize that quickly. So the main under assembles, I will be giving this bit of outlines, the definition, purpose, why do we use assembles, and what are the types of algorithm under this context. And in the end, I will give a little bit of explanation about XGBoost itself. So the definition in a very small word. So assembles in general, they are algorithms that combine several learning methods in order to give a very powerful prediction. So it's like taking a bit of maybe combining different kinds of models together in order to give a very good prediction. And you know that the reason why we do modeling is in order to be able to forecast and to make our forecast as precise as possible. So examples just uses the method of combining several modeling methods in order to give such prediction. So the purpose of modeling in general, not only assembles, the purpose of modeling in general, or any model you might want to build, is in order to reduce bias and also variance. You want to reduce the bias of the model and to reduce the variance. And this is what is popularly known by bias variance trade-off. So you want to find a bit of trade-off between bias and variance. So what does bias mean? If you've done statistics, you know what bias means. So here I gave a little bit of definition what bias really means. So if you have a model and you build your model, you train the model using the training set. Of course, you don't want the model to memorize all the training data, because then it will only perform very well whenever it sees data in the training set. But any other data outside the training set, the prediction will be very, very bad, right? So you don't want your model to memorize all the training sets. So what you want to do is to you don't want your model to, now in this case, in terms of bias, you want to minimize the bias and also reduce the variance. So high bias means that your model do not memorize all the training sets, but a very low bias means that the error between the function of your model and the original function from the training set is very, very small. That's very small bias. That means you have a small bias. The error function between your model itself and the original function from the training set is very, very small. That's small bias, right? But you don't want, you want to find a bit of trade-off between bias and variance. So if you have high bias, if you have a very high bias, then there will be a lot of error in your model. But if you have high variance, then your model will not do well on unseen data sets. So high variance give error, it increases generalization error. With high variance, you have high generalization error. So that is what it means. So you want to reduce both the variance and bias. So they are like two ends of something. So you want to find a kind of midpoint between both the variance, high variance and high bias. You want to find a bit of midpoint between them. So that is the general purpose of modeling, not only here in XGBoost, but generally, you want to do a kind of trade-off between bias and variance. So now, the types of XGBoost that we have the very
Hello,
first one is
please,
bargain.
please. If you say high bias, so high bias is equal to high variance. Is that what you are saying here, sir?
No. That's not what I'm saying. If you okay, let me give
You said high
another.
bias.
Huh?
What I heard from you was high bias is when the model is not training as close to the data set, like it's going far from it. They are saying variance too also means when high variance means
No.
it's very
Okay,
wide
okay.
from the data set.
Let me go over the explanation again. High bias means that when you plot your training points, so the model does not fit well on that training point. That is high bias. You understand what I'm saying? Do you get that?
It does not fit well. That means it does not memorize the data set. Is that what you are saying, yes, sir? Okay.
Yes. That is high bias.
Okay. And high variance too
So
means
are you
the
getting me?
model is learning
So that means your model
can work as
is
far
not
as
flexible
possible.
enough. So high bias means your model is not flexible, that it's not
It's not
memorizing the
flexible.
training set.
I don't
Yes.
understand though. I'm confused.
Okay, I think I'm using too much of terms here. So when we say a model is flexible, that means it passes through all the points in the training set. Do you get what I'm saying? So
Yes,
if
yes, yes.
the model passes through all the points in the training set, that means it has memorized all the points in the training set. And we don't want that because the generalization error will be very high. It won't generalize well because it only knows the training set. It only memorizes the training set. Of course, you have very small error on your training data because if it memorizes all the training sets, then maybe the accuracy will be very, very high, like 99% accuracy. The error is very small. But that is not what you want because any other data outside your training set, it will do woefully, like very bad on any other data outside the training set, right? You get what I'm saying
Yes,
now?
yes. So that is a problem with high bias. That is an high bias time. Anytime it fits perfectly with the training, when it's memorized, is that high bias or low bias?
When it
That's
memorizes the training set, your model has high variance. That is low bias, high variance. You get what I'm saying?
okay, sir. Okay, sir. It has low
Okay.
bias and high variance.
Low bias, high variance. Low bias because it knows all the training sets. So it's not biased. The error there is very, very small. The accuracy is very, very high. But it will have high variance because when you model it on another different set, when you want to predict it using maybe the test set, then the points in the test set it's like it will very, very high away from from your model line. That is what it means because the model line is only memorizing the training set. So in that case, that is low bias, high variance. It memorizes the training set.
Thank
But that
you
is
very
not
much.
what you want. You want a kind of trade-off, a kind of trade-off. You also you want your model to learn also from the training set, right? But you don't want it to memorize it. So you want it to learn from the training set, but you don't want it to memorize it. So to find a trade-off is like you don't want high variance and you don't want high bias. That's what we are saying. Like you are finding a kind of midpoint between bias and variance. So it's like a kind of trade-off between both problem. So I hope that solves your I hope that clarifies it. So so now I'm talking about now the types of algorithm under assembles. The very first one here is the bagging. So the bagging algorithm from the so I will use this pictorial representation to explain it. Let's say you have some observation or a whole lot of data. So what bagging does is to randomly select some of the observation. That is where you see training subset 1. So you randomly select some observation and you train a model on that training subset 1. You get one model. You again go inside the observation, do another random selection, that's training subset 2. You train a different model on that training subset 2. You do that for as many times as possible. So you have, let's say here, you have M models on M different training subsets. So what bagging is now you aggregate all the forecast from the trainings, the model of the first one, second one, up to the M model. So it's like aggregating all the learning, like all the learning from every model. So bagging is like you, so in general, like I said, assembles is like an algorithm whereby you combine different models in order to better your performance, to get a very good performance. So one of it is bagging. And a very popular example of bagging method is the random forest. This is what the random forest does. It randomly selects some observation, train a model on it with different, and decision trees are mostly used in this regards. You can see how it's like it has branches and everything. So this decision tree, and I believe Sebastian already talked about that in the morning a little bit. So now you train different decision trees on different subsets of observation. Then you aggregate the performance of the model. And that is your own, it's like you are combining different models as one. So that is your own, in the end, you only have one model, which is an aggregate of different models trained on different subsets. That is what bagging does. So now the second one, which is boosting algorithm. This is quite different from bagging. What this does is you have your data set, of course. Then you train a model. We call that model a base learner. Like it's like a base learner. Base learner means the very first learner, the very first model on the data set. Of course, when you test that model, you get some error. No model is perfect, right? No model gives you 100%. So you get some error. Then the error, you are not satisfied with the error. You also go back again. Then you retrain the model. Retraining the model means that you want to improve the model and making sure that the error are minimized further. So when you retrain the model, making noting that the first
Usman?
model gives it, yes.
Yeah, just I think the presentation just stopped. So
Oh,
maybe you can check again. Yeah.
okay. Now, okay. Sorry for that. Yeah, I think we are together now.
Yes, it's back.
Yeah.
It's back.
So now this the boosting algorithm, you train a baseline model on the data set. Then usually the baseline model is usually a very weak learner. It's like a very weak learner. because you want to improve it many times until the error you get at the end, you are satisfied with the error. Maybe the error is now small. You can you are satisfied with this small error, then you finish that model. So now in the first, you start with a very weak learner, then you train the weak learner on the data set, you get some error. Then after that, you improve the model as many times as possible until the error at the end, you are satisfied with the error at the end, or the accuracy at the end. So now this is what the boosting algorithm actually does. And one way, an example of boosting algorithm is the gradient boosting. And gradient boosting algorithm uses gradient descent for its parameter optimization. And if you've done a bit of calculus, gradient descent is just like finding the rate of change of a variable with respect to another variable, right? So it's like you are going towards a kind of descent, like you are going towards the minimum point where the minimum area where the error is very, very small. So that's a bit of what gradient descent algorithm does. So it uses derivative to find the it uses derivative for parameter optimization in general. So that is gradient descent for you. So now we can then compare what's bagging and boosting algorithm, what's their similarities and differences. So of course, both they use like a kind of voting method for prediction, or to get the end model. Voting in the sense that let me give an example. Let's say maybe the scores of some students in a class. In order to represent the scores very well, you want to get something that is maybe a kind of how do I say?
Yeah,
How do I say?
I'm sorry,
Like a
sorry, sir.
representation.
Yeah, the
Yes.
presentation just left again. I'm sorry, so just check it. I think
I think
there is
it's
some,
my
yeah.
network. So as I was saying, if let's say you have an example, if you have a class of students where you want to get a representational value for their score, most of us know that the thing to do is just to find the average score of the class, right? That's the main score. That's like a representational value for the scores of the students. But some might say, no, the mean is not representative enough. How about we find the median of the scores, or the mode of the scores, and so on. So what this kind of ensemble method does is, now you say mean, you say median, you say mode. Then let's find a kind of, we want to combine, like we want to have a kind of voting method for all these values, the mean, the median, and the mode, in order to get a particular, just one value that is representational enough. So you might just say, maybe I will take 1/7 of the mean, 1/2 of the variance, and 1/5 of the mode. Then the end result is what I will settle with as a representational score for the students in that particular class. So this is just a kind of idea around ensembles. So now
Did you stop,
XGBoost
or
is,
did you stop, or it left again?
it's same thing. It's just going back and forth. I'm going to continue with my explanation just like until this comes up back. So XGBoost is also an ensemble method. However, what this it's majorly based on boosting algorithm rather than bagging. Its own is on boosting algorithm, and the reason why we have XGBoost is it allows for fast computation. Hopefully, I can get this presentation up as soon as possible. So the XGBoost, it's just a fast gradient boosting algorithm with so many features in it. So you can do gradient boosting, stochastic gradient boosting also. Gradient boosting is just using all the data sets in order to for parameter optimization. While stochastic gradient boosting only uses maybe one data point at a time for its optimization. And you can also do regularized boosting, whereby you penalize the model parameters, and it allows for parallelization. I'm still trying to get my presentation up. And the main advantage for XGBoost is in its speeds and model performance. So in order to understand more about XGBoost, it's just around how the computational, the technical part has been conditioned for speed and model performance. That is, let's see, almost there. So yes, no, I think it's okay. So you can also see XGBoost. Yes, it's fine now. You can see XGBoost also as gradient boosting algorithm, only that it has so many features in it. Rather than doing gradient boosting, you have stochastic gradient boosting, whereby you use just one data point at a time for parameter optimization. You can also penalize your model parameters. It allows for parallelization. Parallelization here means that you can distribute your model running, how it's run on your computer cores, so that it's the speed is executes very fast, and it allows for distributed computing too if you are using it on clusters or anything. So now one thing I'm showing you now is a kind of comparison of XGBoost and other XMBoost method or other algorithm in general. So first you have gradient boosting. So gradient boosting, you can see this is a kind of a small experiment, which is you have this is a classification experiment using different algorithm. So XGBoost, of course, XGBoost gives similar performance as gradient boosting. However, if you check the training time in seconds, you definitely settle for XGBoost, because the training time is comparatively very, very small compared to all other algorithms. The training time is very small. And in all model building technique, you want a very good model that runs very fast. There is this thing called Occam razor. If you have different models that perform the same way, you go for the one with the less complicated model, right? If XGBoost, gradient boosting are performing the same way, of course, maybe, but the training time here matters, because you want your model to run as very fast as possible. You don't want to wait for eternity before you get results. So this is what XGBoost is best at. It gives its execution speed is very, very fast, and it gives comparably high performance in model prediction. So here we have XGBoost, gradient boosting, the random forest, which is an example of the bagging method, and the logistic regression, which is the most popular algorithm we all know, right? This is what we all start with, logistic regression. So if you compare their performance and the training time, that's the running time, you see that XGBoost here is better. And for some years, in the past years, before the advent of deep learning method in machine learning generally, XGBoost has been what has been leading in assemble method. XGBoost leads mostly in Kaggle. If you check Kaggle competition for some couple of years ago, you see models like XGBoost having top rank in the Kaggle competition. This is because of they allow for fast computation and their model performance is comparably very, very high. But now, because of the advent of deep learning, now it's not as used as the deep learning method now. So this is a bit of explanation around assemble method and specifically XGBoost. So I hope you get a bit of understanding about what this is, and if there's any question, we can discuss it.
Yeah, guys, any question to ask about that? I hope you enjoyed the session. So if any question, just ask here or even on Slack. Yeah.
Hello, please. So deep learning, how, like, is it like some people do regression tasks, all those kind of this thing with deep learning? Like, is it normal to do something like that? I used to hear something like they are overusing, like they are overstretching the task or something. So I don't know. Please.
Yeah. One thing is in order to use deep learning, of course, you need the resources because number one, you need a lot of data, and you need computational resources also. So if and sometimes the kind of problem you are dealing with doesn't necessarily require you to use complicated model, right? So I made mention of Occam Razor earlier, which said that if you have two different models performing the same way, like giving you the same model performance, then what you should go with is the simplest one. So if ordinary logistic regression is giving you the same performance as using deep learning with so many layers, deep neural network, and so on. So it's better to go for logistic regression because it's a very simple model and it is interpretable. Most deep learning model have problem of interpretability. You can't really interpret them because you don't really know what's going on in them. So it's difficult for you to explain that this is how it works, this is how it gives the performance and so on. So it's because of the interpretability of most deep learning model, it's better to use simple model if they give the same or equal performance. You get what I'm saying? But now some tasks are so complicated that in order to learn reasonable feature, or in order to learn reasonable thing in some tasks, you need deep learning models, right? But these are high level tasks. Some small level tasks like maybe the one you are doing this week, ordinary hypothesis testing, you don't really need all those models. Or the one you did last week, having to model, some you might need, some you might not need deep learning models. I hope that answer your question.
Great. So I hope it's answered the question of Emmanuel. So any other question from any other people or Emmanuel? I don't know. Yeah. So feel free to continue asking questions on Slack, and we are here to continue answer. Thank you so much.
Please, wait.
Yeah.
Hello, please, where can we learn more about this boosting, how they work, and
okay, so Usman, I think you can check about very good resources online and share with them on Slack. Let's say 2 or 3 good link so that they can still learning more on XGBoost like online.
Yes,
right?
yes, sure.
Okay, sure. So he will share with you, Emmanuel, and thanks for your interest in the topic. Yeah, I really like it. Okay, so let's continue on Slack. Yeah, so I was recording for those who are not